There is a clock ticking right now, not on your wall, not on your wrist, not in your phone sitting on the nightstand beside you. This clock is inside you, inside every atom of every cell of every organ in your body. And it has been running since the moment you were born. In fact, it was running before that. It was running when your parents were born, when their parents were born, when the first human being drew the first breath of anything resembling conscious thought on a cooling African savanna roughly 300,000 years ago. You have never heard this clock. You have never felt it skip a beat or speed up or slow down, because as far as your senses are concerned, it doesn't do any of those things. It moves. It ticks. 1 second becomes 2 seconds, becomes 10, becomes a year, becomes a lifetime. And from inside the stream of that ticking, everything feels perfectly smooth, perfectly consistent, perfectly real. But here is what nobody told you in school. Here is the thing that sits underneath all of modern physics, like a fault line underneath a city, present, enormous, capable of rearranging everything, but invisible until the ground starts to move. That clock is not keeping the same time as the universe, not even close. Right now, somewhere in the solar system, a satellite launched by human hands is orbiting Earth at roughly 14,000 kilometers per hour. The GPS system, the one your phone uses to navigate to the nearest late-night restaurant or to track your morning run, depends on clocks aboard those satellites. And here is the part that most people who use GPS every single day of their lives have never been told. Those clocks run fast. Not because they were built poorly, not because of a manufacturing defect. They run fast because time itself passes differently up there than it does down here, by about 38 microseconds per day. 38 millionths of a second. That sounds like nothing. That sounds like a rounding error. That sounds like something you could safely ignore. But if the engineers who built the GPS system had ignored it, if they had said, well, 38 microseconds a day, that's not worth worrying about, your navigation would drift by roughly 10 kilometers every single day. Within a week, you'd be told to turn onto roads that don't exist. Within a month, the entire system would be useless. Within a year, it would be off by enough to misplace you by the width of a small country. So the engineers don't ignore it. They correct for it. Every day, every GPS satellite on the planet compensates for the fact that time runs differently in orbit than it does on the ground. And they do this not because it's a quirk of the technology. They do it because it's a law of nature. A law that, when you start to understand it, truly understand it, not just repeat the words but feel the weight of the idea, changes what you thought you knew about the universe you are sleeping inside of right now. This is a video about time, not in the casual philosophical sense, and not a meditation on how quickly the years go by or how differently time seems to move when you're bored versus when you're happy. Those are real experiences and they matter, but they're not what we're here for tonight. Tonight, we are going in much deeper than that. Tonight, we are going to follow time out past the atmosphere, past the orbit of the moon, past the orbit of Jupiter and Neptune and the scattered disk of icy debris at the edge of the solar system, out into the interstellar medium, out toward other stars, out into the geometry of space-time itself. And we are going to find out what happens to a second when you take it somewhere it has never been. Because the answer is not what you expect. Let's start at the beginning. Or rather, let's start with the person who first realized there was a problem. Albert Einstein was 26 years old and working as a patent clerk in Bern, Switzerland in 1905, when he published 4 papers that, in retrospect, qualify as one of the most remarkable intellectual explosions in the history of human thought. One of those papers introduced the special theory of relativity. It was not long and it was not filled with complicated mathematics by the standards of theoretical physics. Einstein himself described the core insight as simple enough that it could be explained to any patient student in a single afternoon. The insight was this: the speed of light is the same for all observers, no matter how fast they are moving. That sentence is easy to read. It is very hard to believe, because it violates something that feels intuitively obvious about the world. Let's say you are standing still, and you throw a ball at 20 kilometers per hour. Now, let's say you are running at 10 kilometers per hour, and you throw the same ball at the same speed relative to you. A stationary observer watching you run would see the ball moving at 30 kilometers per hour, 20 from the throw plus 10 from your running. This is how velocity addition works. This is how it works for every object we have ever observed in everyday life. This is how it worked for Galileo and Newton, and every physicist and engineer who came before Einstein. But light doesn't work this way. If you fire a beam of light from a stationary position, it travels at approximately 300,000 kilometers per second. If you fire a beam of light from a spacecraft moving at half the speed of light, it still travels at 300,000 kilometers per second, not 1.5 times that, not some fraction more or less, exactly the same. A person on the ground watching the spacecraft and a person on the spacecraft both measure the light moving at the same speed. This is not an opinion. This is not a theoretical preference. This is the result of over a century of experimental verification, and it is accurate beyond any measurement technology we currently possess. Now, here is the problem. If the speed of light is constant for all observers, and if speed is distance divided by time, then for all observers to agree on the speed, they cannot all agree on the distance, and they cannot all agree on the time. The only way to keep the speed of light the same for everyone is to let distance stretch and compress, and to let time stretch and compress, depending on how fast you are moving. This is not a metaphor. It is not a thought experiment. It is physics. Time itself, the interval between one moment and the next, the gap between a tick and a tock, changes based on your velocity and your position in a gravitational field. And this changes everything. There are 2 mechanisms by which time runs differently in different parts of the universe. Einstein discovered both of them in sequence, the first in 1905 as part of special relativity, the second in 1915 as part of general relativity. The first is velocity. The faster you move, the slower your time passes relative to a stationary observer. This is called time dilation, and the mathematical relationship is elegant. As your velocity approaches the speed of light, your time slows toward 0. At exactly the speed of light, which only massless particles like photons can achieve, time would stop entirely. From the photon's perspective, if it had one, no time passes between its creation and its absorption. A photon leaving the surface of the sun and traveling for 8 minutes to reach your eye experiences no time at all. The 8 minutes exist only for observers who are not moving at the speed of light, for objects with mass, for anything made of matter, including you, including every spacecraft we have ever built. The speed of light is a wall you can approach but never reach. but you don't have to reach it for the effect to matter. Even at the modest velocities available to modern spacecraft, time dilation is real and measurable. The second mechanism is gravity. The closer you are to a massive object, a planet, a star, a black hole, the slower time passes relative to an observer farther away. This is called gravitational time dilation, and it is the effect that makes those GPS clocks run fast. The satellites are farther from Earth's center of mass than you are, so they experience slightly weaker gravity, and their clocks tick slightly faster, roughly 45 microseconds per day, faster due to gravity alone. But they are also moving quickly in their orbits, which slows their clocks by about 7 microseconds per day due to velocity. The net result, 38 microseconds fast per day. Both effects are real. Both must be corrected for every day. Now, hold those two numbers in your mind because we are about to start scaling them up. 38 microseconds per day sounds trivial, but we are not going to stay near Earth. We are going to follow time out across distances that make Earth's orbit look like a step in a hallway, and we are going to watch what happens to those numbers as the distances grow and the gravity changes and the velocities increase. We are going to find that a second is not a second in the way you always assumed. Not out there, not everywhere, not always. Before we leave Earth's neighborhood, let's make sure we have a firm grip on what we are measuring and why it matters. When physicists talk about time dilation, they are talking about something called proper time, the time measured by a clock that travels along with you in your own reference frame. Your heartbeat, your atomic clock, your biological aging, all of that happens on your proper time, and your proper time is real. There is nothing illusory about it. The issue is that your proper time is not the same as someone else's proper time, if they are moving differently than you or sitting in a different gravitational field. This has an immediate biological implication that is not science fiction. If you were to travel to a massive object and back, you would genuinely, physically, age less than the people you left behind. Not metaphorically, not in a way that only a clock would notice. Your cells would have divided fewer times, your telomeres would be fractionally longer, your neurons would have fired fewer cycles. You would be, in every measurable physical sense, younger than people who stayed home, even if you were born on the same day as them. The effect at the velocities and gravity fields currently accessible to human technology is tiny, but it exists. It has been demonstrated. In the 1970s, physicist Joseph Haffel and astronomer Richard Keating flew cesium atomic clocks around the world on commercial airplanes and compared them to clocks that stayed on the ground. The flying clocks showed less elapsed time, consistent with predictions from both special and general relativity. The effect was small. The physics was real. Now let's scale up. Let's take a trip, not in a spacecraft, but in imagination, which is where all of physics ultimately lives before the engineers catch up. You are in a theoretical craft capable of accelerating to a significant fraction of the speed of light. Let's say, for the purposes of this exercise, that you can reach 10% of the speed of light, roughly 30,000 kilometers per second. No existing human technology approaches this, but it's a useful starting point for understanding how the numbers scale. At 10% of the speed of light, the time dilation effect is small but measurable. For every year that passes for you aboard the spacecraft, roughly 1.005 years passes on Earth. 0.5%, Not dramatic, you'd age very slightly less than the people back home, and the difference would be in the range of a few days per year. Now, push that to 50% of the speed of light, half the speed of light. This is an extraordinary velocity. Nothing we have ever launched even approaches 100th of this speed, but theoretically possible for an object with mass, given sufficient energy. At 50% of the speed of light, time dilation becomes significant. For every year you experience, about 1.15 years pass on Earth. For a 10-year journey at that speed, you'd be roughly 1.5 years younger than someone who stayed home when you returned. Still not enormous. But you are now genuinely, measurably, irreversibly diverging from Earth's timeline. Pushed to 90% of the speed of light. For every year you experience, 2.3 years pass on Earth. A 10-year journey at this speed means more than 23 years have passed at your destination. You leave as a young adult. You return to find that a generation has grown up in your absence and you have aged only 10 years. Push to 99%. Now, for every year you experience, more than 7 years pass on Earth. Push to 99.9%. For every year you experience, more than 22 years pass on Earth. Push to 99.99%. More than 70 years per year of your time. Push to 99.999999% of the speed of light. A single year of your proper time corresponds to roughly 23 million years of external time. You travel for what feels like a year. You return to Earth. 23 million years have passed. Every human being you ever knew is not just dead. They are fossils. Civilizations have risen and collapsed. Species have evolved. The coastlines of the continents you knew have shifted. The sun has burned through a fraction of its remaining hydrogen. Everything you called home is an archaeological layer somewhere beneath the new surface of a planet that has been continuously reinvented for 23 million years. And you are 1 year older. This is the clock you were never told about. Not a metaphor, not a science fiction premise. A physical reality that sits underneath the comfortable, consistent, familiar flow of seconds and minutes and hours that you have been living inside for your entire life. The reason it has never disrupted your life is that the effect is only dramatic at velocities and gravitational gradients that no human being has ever experienced at meaningful scale. But the universe doesn't care about the limits of our technology. The universe is full of places and processes where these effects are not merely measurable but defining, where they determine the structure of reality itself. We are going to visit some of those places tonight. We are going to follow time through the solar system, out to the nearest stars, into the extreme environments near stellar mass and supermassive black holes, back to the first moments of the universe itself, and forward to the last moments before the final silence. And in each of those places, we are going to check what the clock says. Not the clock on the wall, not the clock on your phone, the real clock, the one embedded in the geometry of space-time that governs how fast or slowly the universe is passing for anything that exists at that location. Because once you have that clock in your mind, the universe never looks the same again. It is no longer just vast. It is no longer just old. It is a place where time itself is a variable, where the same moment experienced in two different locations means something genuinely different. Where a second on Earth and a second near the event horizon of a black hole are connected by physics, but divided by an unbridgeable gulf of experienced reality. Let's begin that journey close to home, closer than you might expect. Right now, As you lie here and breathe and listen, you are in motion, not just relative to the ground beneath you, which is rotating with the Earth at roughly 1,700 kilometers per hour at the equator, though that is true, but relative to the center of the Earth. You are sitting in a gravitational field that is weaker at the surface than at the center, which means time runs very slightly faster for you than for a hypothetical observer sitting at Earth's core. Relative to the Sun, Earth is orbiting at roughly 30 kilometers per second, which introduces a velocity-based time dilation between Earth and a hypothetical stationary observer outside the solar system. Relative to the center of the Milky Way galaxy, the entire solar system is orbiting at roughly 230 kilometers per second. This is not a small velocity. It is not something we feel or notice, but it is real, and it has implications for the comparison of clocks between the solar system and hypothetical observers in regions of the galaxy with different orbital velocities. The universe is not a place of still points from which time runs evenly in all directions. It is a topology, a geometry of varying densities, varying velocities, varying gravitational fields, and in every region of that topology, time runs at its own rate, keeping its own proper time, ticking out its own version of the seconds that feel so absolute from inside your particular corner of the local universe. And we have barely left the driveway. In the next part, we are going to leave the Earth-Moon system and move into the deeper solar system, where the Sun's gravity begins to stretch and compress time in ways that become relevant to any serious discussion of long-duration space travel. We are going to discover that the Voyager probes, the farthest objects ever launched by human civilization, are experiencing time at a rate that is measurably different from the rate at which time passes on Earth. We are going to find that the famous twin paradox of special relativity is not a paradox at all, but a precise prediction of what would happen to any two people separated by velocity and then reunited, and what it would mean to be the one who travelled. But before we get there, close your eyes for a moment if they aren't already. Think about that GPS satellite overhead. Think about the 38 microseconds a day corrected for every day by engineers who took Einstein seriously when the rest of the world thought he was describing something abstract and philosophical. Think about the fact that the device in your hand, the one you use to find parking and order delivery and navigate the streets of every city you have ever visited, depends for its accuracy on the precise measurement and correction of the difference in time between the surface of the Earth and the orbit 300 kilometers above your head. Think about the fact that time dilation is not a theory waiting to be confirmed. It is a product feature. It has been corrected for in a consumer product used by billions of people every day. And what we have talked about so far is the smallest, most accessible edge of an effect that scales up, without limit, without ceiling, into the most extreme environments in the universe. We are standing at the beginning of the timeline. The clock is ticking. The scale of what is coming makes everything we have described tonight look like the first second of a countdown that runs for longer than you currently have a framework to imagine. Stay with it. We are just getting started. There is a place roughly 21 billion kilometers from where you are lying right now, where a machine built by human hands is traveling through space at about 17 kilometers per second. It has been traveling since 1977. It was launched the year that the first Star Wars film played in theaters, the year that the Apple II personal computer went on sale, the year that most of the people currently alive on Earth were either very young children or not yet born. And it is still going. It has not stopped. It has not slowed in any meaningful way. It has crossed the boundary of the heliosphere, the bubble of solar wind and magnetic influence that defines the edge of the sun's direct reach, and it is now moving through interstellar space, the first human-made object in history to do so. Its name is Voyager 1. And right now, tonight, as you listen to this, Voyager 1's clock is running at a slightly different rate than your clock. Not because something went wrong, not because the hardware degraded, because it is moving faster than you, and because it is sitting in a weaker gravitational field than you, and because those two facts, those two physical realities that Einstein spent the better part of 2 decades formalizing into the most tested theory in the history of science, mean that the proper time aboard Voyager 1 is not the same as the proper time in your bedroom. The difference is small. We are talking about fractions of a second accumulated over decades, but the principle is absolute, and we are here tonight to follow that principle out to where it stops being a small correction and starts being the dominant fact of physical reality. So, let's travel. Let's start with the moon, then push outward through the solar system station by station, watching what happens to the clock as we go. The moon is the most familiar object in the night sky, and the only place beyond Earth that human beings have ever physically stood. 12 of them did, between 1969 and 1972, and none of them were told before they left that time would pass differently on the lunar surface than it did back home in Houston. It passes faster. The moon is farther from the Earth's center of mass than the surface of the Earth is, which means it sits in a weaker gravitational field. Weaker gravity means clocks run faster. This is the gravitational time dilation we established in the first part of this journey. A clock on the lunar surface gains approximately 56 microseconds per day relative to a clock on Earth's surface, primarily due to the weaker gravity. The moon also moves at a different velocity in its orbit, which partially offsets this, but the net result is that time runs faster on the moon than on Earth. 56 microseconds per day. Over the course of a full year on the moon, you would have aged approximately 20 milliseconds more than someone who stayed on Earth. Your cells would have undergone slightly more division cycles. Your heartbeats would number fractionally more. The effect is small enough that no astronaut has ever noticed it biologically, and the Apollo missions were short enough that the accumulated difference was in the range of microseconds. But it is real, it is there, and it scales. Now, let's keep going. Mars sits at roughly 1.5 times Earth's distance from the Sun, and its gravity at the surface is about 38% of Earth's gravity. Lower gravity, combined with a slightly different orbital velocity, Mars moves slower than Earth because it sits in a wider orbit, means that clocks on Mars run faster than clocks on Earth by a total of approximately 24 microseconds per day. Slightly less than the moon's advantage because Mars has more surface gravity than the moon, pulling time back toward Earth's rate. If you were a colonist on Mars, and there are people alive right now who believe they will be within their lifetimes, and you stayed for a full year before returning to Earth, you would return having aged roughly 8.5 milliseconds more than your counterpart who stayed home. Not noticeable, not biologically meaningful at these timescales. But here is the thing about these numbers. We are still inside the inner solar system. We are still close to the Sun. The gravitational and velocity effects that define the time rate in this region are still within the range of what feels like a unified solar neighborhood, a single system with a single dominant gravitational influence and velocities that, though fast by human standards, are modest fractions of the speed of light. Let's push outward. Jupiter is 5 times farther from the Sun than Earth. It is the largest planet in the solar system, containing more mass than all the other planets combined. Its gravity at the cloud tops is roughly 2.5 times Earth's surface gravity. Any spacecraft orbiting close to Jupiter, and we have sent several, including the Galileo probe and the currently active Juno mission, is sitting in a significantly deeper gravitational well than anything orbiting Earth. In a deeper gravitational well, time runs slower. For an object in low Jovian orbit, say a future crewed station positioned above Jupiter's clouds, time would run slightly slower than on Earth rather than faster the way it does on the Moon and Mars. The planet's enormous mass overwhelms the reduced distance to Sun effect. The result is a gravitational time dilation deficit relative to Earth of a few tens of microseconds per day, depending on precise orbital altitude. This is interesting for a different reason than the Moon and Mars numbers. It tells us that the relationship between location and time rate is not linear, and it is not monotonic, meaning it doesn't just keep going in one direction as you move farther from the Sun. It depends on the specific, local gravitational environment. A habitat near a massive planet can experience slower time than one farther from any planet at all, purely because of the local gravitational influence. The universe is not a smooth gradient of time. It is a landscape, a topography of time rates defined by the distribution of mass and the velocities of objects moving through that mass distribution. Every massive body creates a depression in the time landscape. Every high-velocity environment creates a compression. And the universe is full of massive bodies and high velocities that make everything in our solar system look gentle and simple. Voyager 1 is now beyond the reach of any planet's significant gravitational influence. It is in interstellar space, in a region where the dominant gravitational influence is the distant and diffuse pull of the galactic center rather than any nearby stellar or planetary body. The gravitational field out there is extraordinarily weak compared to anything we experience on Earth. Weaker gravity means clocks run faster. But Voyager 1 is also moving at 17 kilometers per second relative to Earth. That velocity introduces a time dilation effect. Clocks in motion run slower. Relative to a stationary observer outside the solar system, Voyager 1's clock is subject to both effects. Faster due to weak gravity, slower due to velocity. At 17 kilometers per second, which is roughly 0.0057% of the speed of light, the velocity time dilation is tiny. The gravitational effect at that distance from the Sun and any massive body is also tiny. The two effects partially cancel each other. The net result is that Voyager 1's clock is running at a rate that differs from Earth's clock by an almost immeasurably small amount per day. And yet, it differs. In the 47-plus years since Voyager 1 launched, the accumulated difference between its clock and ours is in the range of fractions of a second. Nothing. Nothing that would matter to any mission parameter. Nothing that a human being could feel. But we are not stopping at Voyager 1. Let's talk about what lies between the solar system and the next star. Because this is where the intuition begins to break down and where the implications of what we've been discussing start to take on a different quality. The nearest star system to Earth is Alpha Centauri, actually a triple system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, the last of which holds the title of closest individual star at approximately 4.24 light-years from Earth. A light-year, as a reminder, is the distance light travels in 1 year, roughly 9.5 trillion kilometers. The distance to Proxima Centauri is approximately 40 trillion kilometers. Voyager 1 is traveling at about 17 kilometers per second. At that speed, it would take approximately 75,000 years to reach Proxima Centauri if it were heading in that direction, which it isn't. But let's say a future probe, launched with the most advanced propulsion we can theoretically imagine deploying within this century, could reach 1% of the speed of light, about 3,000 kilometers per second. That's more than 150 times faster than Voyager 1. At 1% of the speed of light, the journey to Proxima Centauri would take about 420 years. At 10% of the speed of light, a truly extraordinary velocity requiring energy budgets that dwarf anything in current human capability, the journey takes about 43 years. At 10% of the speed of light, time dilation is approximately 0.5%. Over a 43-year journey, the crew of that spacecraft would age roughly 2.5 months less than people back on Earth. Small. Interesting, but small. But here is where the physical reality of interstellar travel begins to truly diverge from human intuition. The problem is not just the time dilation at the cruising speed, the problem is the relationship between the journey time and the distance when you start pushing the velocity high enough for dilation to matter significantly. Imagine a spacecraft capable of continuous acceleration at 1g, roughly the gravitational pull you feel right now, lying where you are. 1g of continuous acceleration is gentle enough that the crew would feel entirely normal. Their bodies would experience the same pull they've always felt. And yet, if you maintain 1g of acceleration for long enough, the relativistic effects become staggering. After 1 year of 1g acceleration, you are traveling at about 77% of the speed of light relative to your starting point. Time dilation at that speed is significant. For every year, the crew experiences about 1.5 years pass on Earth. Manageable. After 2 years of your proper time at 1g, you are approaching 86% of the speed of light. For every year you experience, roughly 2 years pass on Earth. After 3 years of your proper time, 94% of c, external time passing at roughly 3 years for every one of yours. After 4 years of your proper time, you are at about 97% of c. External time has passed at about 4 times the rate of your internal experience. You have been accelerating for what feels to you like 4 years, and roughly 16 years have passed on Earth. Now flip the engines to decelerate for another 4 years of your proper time. You have spent 8 years of your life, 8 years of meals and sleep cycles and conversations and heartbeats. You have travelled to a destination roughly 27 light-years away, and on Earth, approximately 50 years have passed. You left in your 30s. You return, or you arrive, because going back would require another 8 years of your proper time and another 50 years of Earth time to find that everyone you knew when you left has aged beyond recognition or died. And you have travelled to what? The nearest stellar neighbourhood, not a galaxy away, not to the edge of the observable universe, just to the next handful of stars over. The ones that on the scale of the Milky Way are essentially our local neighbours, practically next door. This is the moment in the journey where the emotional weight of what we are discussing becomes hard to hold in one thought. Because What we are describing is not the science fiction trope of the time-traveling hero who zips around the galaxy and comes back unchanged. What we are describing is a one-way door. Any human being who travels at relativistic speeds is not traveling in the same stream of time as the civilization they left behind. They are stepping onto a different timeline, not a fictional, alternate universe, not a philosophical abstraction, but a genuinely separate track of experienced reality measured in proper time. The person who stays on Earth and the person who travels are not just separated by distance. They are separated by the fundamental currency of existence, the seconds that constitute a life. And this separation cannot be undone. It is not like a time zone difference that you correct when you land. It is irreversible. The traveller cannot get those years back. The people back home cannot get them back either. The divergence, once created by velocity and gravity, is permanent, written into the physical aging of every cell, every atom, every particle that makes up the body of the traveller and the body of the one who waited. There is a thought experiment in physics called the twin paradox that makes this concrete. Imagine two identical twins, same age, same biology, same moment of birth. One stays on Earth, one travels to a distant star at a significant fraction of the speed of light and then returns. When they reunite, the travelling twin is younger, not metaphorically, not in terms of how they feel, biologically, physically, measurably younger. The twin who stayed on Earth has aged more. This is the twin paradox. It is called a paradox because there is a naive argument that says, from the travelling twin's perspective, wasn't it the Earth twin who was moving? Shouldn't it be symmetric? Shouldn't they both be the same age when they reunite? The answer is no, and the reason is that the situation is not symmetric. The travelling twin undergoes acceleration. They turn around. The act of turning around, of reversing direction, breaks the symmetry between the two reference frames. The Earth twin never accelerates. The travelling twin does. This introduces a genuine physical asymmetry, and the result is genuine biological asymmetry. The traveller is younger. No paradox, just physics, just the clock you were never told about. Now, let's take everything we've learned in the solar system and at the interstellar scale and start pressing towards something even more extreme. Because while the effects we have described so far are real and measurable and philosophically profound, they are still operating in what a physicist would call a weak field, low-velocity regime. The really dramatic time dilation, or the kind that doesn't just make you a few years younger, but a few million years younger, requires one of two things: either speed so close to light that the fraction of a percent margin becomes everything, or gravitational fields so intense that the curvature of space-time near a massive object does to time what the edge of a drain does to water. The most extreme gravitational time dilation environments in the known universe are found near black holes. And this is where the countdown begins to take on its most extreme form, because near a black hole, time doesn't just run differently. It approaches a limit. It approaches in the direction of the event horizon something that, from the outside, looks like time stopping altogether. Think about what that means for a moment in the context of everything we have built up so far. We started with GPS satellites losing 38 microseconds a day. We moved through the Moon gaining 56 microseconds a day, Mars gaining 24, Jupiter's orbit losing a small fraction relative to Earth. We travelled out to interstellar space where at 10% of the speed of light, you age a few months less over a 40-year journey. We pushed to relativistic velocities where the divergence becomes years, then decades, then generations. And now we are approaching the place where the divergence becomes not years or generations, but the entire future history of the universe. Near the event horizon of a sufficiently massive black hole, time dilation becomes so extreme that an outside observer watching a clock fall toward the event horizon would see that clock appear to slow down, redshift, and, asymptotically, never actually reaching the horizon from the external perspective, appear to freeze. The clock never appears to cross the horizon. It approaches the crossing and slows and slows and slows, and the light carrying the image of that clock stretches and reddens and fades. And the last impression you have of it is a ghostly, frozen image of a clock at the moment of near crossing, slowly dimming toward invisibility. From inside that clock's reference frame, from the perspective of whatever is riding along with it, the crossing happens in finite, proper time. The infalling object does cross the horizon. It does continue into the interior, but the external universe, watched from inside, appears to run forward at an extraordinary rate. The infalling observer would see the external universe compressed into a blinding, accelerated blur as their proper time approaches the horizon. From their perspective, not frozen, racing. We will spend the next part of this journey exploring exactly what black holes do to time and why the region near a black hole is not just an extreme environment in the physical sense, extreme temperature, extreme gravity, extreme tidal forces, but an extreme environment in the most fundamental sense possible. A place where the river of time runs at a rate so different from ours that the gap between 1 second experienced there and 1 second experienced here is not a rounding error, not a GPS correction, not a biological curiosity. It is the distance between one universe and another. But before we leave the solar system behind, let's stay here one more moment. Let's think about what we have covered and what it means for the timeline we are counting down. The solar system is 4.5 billion years old. The Sun has approximately 5 billion years of hydrogen-burning life remaining before it enters its red giant phase and eventually destroys the inner planets, a topic for another countdown, another night. But those 5 billion years are not simply 5 billion identical Earth years stacked on top of each other like bricks. They are 5 billion years measured by whose clock, at what velocity, at what distance from what mass. An observer near the surface of the Sun in an extremely hot and lethal but theoretically conceivable location would experience time running slower than on Earth due to the Sun's gravitational field by about 2 seconds per century. Tiny, but real. In 5 billion years, an observer somehow surviving at the Sun's surface would have experienced about 3 years less of proper time than an observer on Earth. Meanwhile, an object in the very far outer solar system, past Neptune, in the Oort cloud where comets originate, at 10,000 times Earth's distance from the Sun, would be sitting in an exceptionally weak gravitational field, experiencing time running very slightly faster than on Earth. Not dramatically, not in a way that changes any timeline in a meaningful way at that scale, but the principle is there and it is inviolable. There is no single clock for the solar system. There is no master timer that all objects in the solar system are synchronized to. Every object keeps its own time, and the differences between those times are governed by physical laws that have been tested to extraordinary precision. The universe does not have a universal clock. It has never had one. What we call the present moment, The shared now that feels so obvious and inevitable from inside the cozy bubble of human experience is a local phenomenon. It is real for us here, in this gravitational field, at this orbital velocity, on this particular spinning rock. But it does not extend outward without change. By the time you reach the orbit of Jupiter, the now is already slightly different. By the time you reach the nearest star, the now has become something genuinely alien. By the time you reach the event horizon of a black hole, the now has become a concept so stretched and distorted that the word itself barely applies. This is what physics tells us. This is what the math predicts, and what the experiments confirm, and what the engineers who built your GPS system have been compensating for, quietly, every day, for decades, without ever making much of a fuss about it. The clock is different everywhere you go. We are going to the edge of the most extreme objects in the universe. We are going to where time slows towards zero. In 2014, a film called Interstellar depicted something that most audiences assumed was creative license. A crew of astronauts descends to the surface of a planet orbiting close to a supermassive black hole. They spend approximately 3 hours on the surface. When they return to their ship waiting at a safe distance, they find that their colleague aboard the ship has aged 23 years. He is an old man. They are unchanged. He hands them decades worth of video messages from home, children grown into adults, grandchildren born, entire lives lived in the span of what felt to the landing crew like a long afternoon. Most people watching that scene assumed it was science fiction exaggeration. A dramatic device, something borrowed loosely from Einstein to give the plot emotional weight. It was not exaggerated. The physics depicted in that scene, consulted on by Nobel Prize-winning physicist Kip Thorne, who later wrote an entire book about the science behind the film, was not only accurate in principle, but conservative in practice. The filmmakers actually dialed back the effect because the true numbers, applied faithfully, would have produced a time dilation ratio so extreme that audiences would have assumed it was fantasy. The real physics, near a sufficiently massive, sufficiently close black hole, would produce not 23 years of external time for every 3 hours of your time, but potentially thousands of years, millions. Depending on how close you get and how massive the black hole is, the ratio of external time to your experience time can become effectively unbounded. Let's build up to that carefully, because this is the part of the journey where time stops being a background fact of the universe and becomes the defining, overwhelming, terrifying feature of the landscape. Near a black hole, time is not something that happens around you. It is something that is being done to you, stretched and compressed and redirected in ways that have no analogue in any experience any human being has ever had. First, let's establish what a black hole actually is in terms that matter for our purposes tonight. A black hole is a region of space-time where mass has been concentrated to such a degree that the gravitational field exceeds the escape velocity of light. Nothing that enters the region defined by the event horizon or the spherical boundary around the singularity can escape, because escaping would require exceeding the speed of light, and nothing with mass can do that. Beyond that boundary, all paths in space-time curve inward. There are no outward trajectories. The interior of a black hole is not just a place with very strong gravity. It is a place where the geometry of space-time has been so severely warped that the concept of moving outward has been eliminated from the set of available options. The event horizon is not a physical surface. There is no wall there, no membrane you would feel as you crossed it. If you were falling freely toward a stellar mass black hole, you would cross the event horizon without any immediate physical sensation. The tidal forces that would eventually shred you apart would become significant later, closer to the singularity. The horizon is a geometrical boundary, a point of no return defined purely by the structure of space-time, and it is at and near this boundary that time dilation reaches its most extreme values. The mathematics of gravitational time dilation near a black hole comes from Einstein's general theory of relativity, specifically from the solution worked out by German physicist Karl Schwarzschild in 1916. Reportedly derived while Schwarzschild was serving on the Russian front during the First World War, doing theoretical physics in the margins of military correspondence. He sent the solution to Einstein, who was reportedly astonished that an exact solution existed. The Schwarzschild solution describes the geometry of space-time around a non-rotating, uncharged spherical mass, the simplest case of a black hole. The mathematics predict that as you approach the Schwarzschild radius, the distance from the center at which the escape velocity equals the speed of light, which is the event horizon for this type of black hole, the ratio of your experience time to external time approaches zero. Not gradually, not linearly, asymptotically, as a limit. Approaching zero without ever quite reaching it from the perspective of an outside observer, and reaching it in finite proper time from the perspective of the infalling observer. Let's put some numbers to this. The time dilation factor near a black hole depends on how close you are to the event horizon, expressed as a ratio of your distance to the Schwarzschild radius. If you are at twice the Schwarzschild radius, twice the radius of the event horizon, time runs for you at about 58% of the rate it runs far from the black hole. For every 100 seconds that pass for you, roughly 170 seconds pass in the external universe. At 1.5 times the Schwarzschild radius, you are at the photon sphere, the region where light itself orbits the black hole. At this distance, time dilation is severe. For every hour you experience, roughly 3.5 hours pass externally, push closer. At one point, 1 times the Schwarzschild radius, just 10% above the event horizon, time dilation becomes extreme. For every hour you experience, roughly 3 hours and 20 minutes pass externally. That doesn't sound dramatic yet. Let me give you the right version of the formula because the effect becomes extreme in a way that requires precise language. At 1.01 times the Schwarzschild radius, just 1% above the event horizon, for every hour you experience, roughly 10 hours pass externally. For every day you experience, nearly 2 weeks pass for the universe outside the black hole's influence. At 1.001 times the Schwarzschild radius, 0.1% above the event horizon, for every hour you experience, roughly 32 hours pass externally. For every day you experience, about a month passes outside. At the event horizon itself, at the Schwarzschild radius exactly, the time dilation factor becomes infinite. Your time stops relative to external time. From outside, you appear frozen at the moment of horizon crossing. You never appear to cross. Your image fades, reddens, and asymptotically approaches but never reaches the moment of entry. From your own perspective, if you could somehow survive the journey to the horizon, time continues normally up to and past the crossing. But the universe outside has, in the moment of your crossing, reached its infinite future. Now let's talk about the specific black holes that exist in the universe we actually live in, and what these numbers mean in practice. Stellar mass black holes form when massive stars, those with initial masses roughly more than 20 times that of the Sun, exhaust their nuclear fuel and collapse. The resulting black holes typically have masses between roughly 5 and 20 times the mass of the Sun, with event horizons ranging from about 15 to 60 kilometers in radius. There are believed to be hundreds of millions of stellar mass black holes in the Milky Way alone, though we have only identified a relative handful because isolated black holes that aren't actively consuming matter are nearly impossible to detect. Supermassive black holes are a different category entirely. Every large galaxy appears to have one at its center. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million times the mass of the Sun. Its event horizon has a radius of about 12 million kilometers, roughly 17 times the radius of the Sun. If you replace the Sun with Sagittarius A star, its event horizon would extend about a third of the way to Mercury's orbit. And then there are the truly extraordinary cases. The black hole at the center of the galaxy, M87, the first black hole ever directly imaged, the one whose photograph was released in 2019 and circled the world as one of the most astonishing images ever captured by human instruments, has a mass of approximately 6.5 billion times the mass of the Sun. Its event horizon has a radius of roughly 19 billion kilometers, larger than our entire solar system, out to well beyond Neptune's orbit. TON 618, a quasar located about 10 billion light-years from Earth, contains a black hole with a mass estimated at 66 billion solar masses. Its event horizon is so large that light takes days to cross it. These numbers are almost impossible to hold in the mind as spatial realities. But for our purposes tonight, they matter for a different reason. The size of a black hole determines the tidal forces near the event horizon. For a stellar mass black hole, the tidal forces near the horizon are so extreme that any human body, or any solid object of human scale, would be shredded into individual atoms long before reaching the horizon. But for a supermassive black hole, the tidal forces at the horizon are actually gentle. The radius is so large that the gradient of gravity across the distance of a human body is modest. A person could theoretically cross the event horizon of M87 star's black hole without feeling any particular physical sensation at the moment of crossing. They would not know they had entered a region of no return. What they would know, if they had been monitoring their external communications, is that the universe outside had been running at an extraordinary rate for the entire duration of their approach. Every second of their experienced time, years would have passed outside. Every minute, decades. Every hour, centuries. This is where the interstellar scenario stops being movie drama and becomes physics homework. The black hole depicted in that film, called Gargantua, was modelled on a maximally spinning black hole of supermassive scale, approximately 100 million solar masses. Spinning black holes are described not by the Schwarzschild solution, but by the Kerr solution, worked out by New Zealand mathematician Roy Kerr in 1963. Spinning black holes have a more complex geometry. They drag space-time around them in a phenomenon called frame dragging, and they allow for stable orbits closer to the event horizon than non-spinning black holes do. Kip Thorne calculated that for the planet in the film, called Miller's planet, to orbit close enough to the black hole to experience the time dilation depicted, the black hole would need to be spinning at very close to its maximum possible spin rate. The orbit would need to be extraordinarily tight. The time dilation ratio of approximately 60,000 to 1 hour on the planet equals roughly 7 years for the universe outside the black hole's influence, is physically achievable under those conditions. It is not fictional. It is the result of plugging the relevant orbital parameters into the Kerr metric and reading off the time dilation factor. 1 hour equals 7 years. 3 hours on the surface equals 21 years outside, which is close to, but not exactly, the 23 years depicted in the film, the difference absorbed into the specific orbital parameters and the time spent travelling down to the surface and back. 7 years per hour. Let's sit with that for a moment. If you were to take a nap on Miller's planet, say 8 hours of sleep, you would wake up 56 years later by the outside universe's reckoning. A child born the night you fell asleep would be middle-aged when you opened your eyes. The technological landscape of the civilization that launched your mission would have transformed, potentially beyond recognition. Wars would have been fought and ended. Generations would have turned over. The people who trained you and briefed you and sent you off might be dead, and you would have had a good night's sleep. Now, let's take the time dilation effect of black holes and connect it to the countdown structure that underlies everything we are exploring in this channel. Because one of the most profound implications of extreme time dilation near black holes is not what it means for hypothetical space travelers. It is what it means for time itself as a cosmic variable, and for the question of when things happen in the universe. Consider this: the supermassive black hole at the center of the Milky Way, Sagittarius A star, is about 26,000 light-years from Earth. There are stars orbiting Sagittarius A star at distances close enough that they experience significant, though not extreme, gravitational time dilation relative to Earth. One of the most studied of these, a star called S2, has an orbital period of about 16 years and comes within about 120 astronomical units of the black hole, roughly 4 times the distance from the Sun to Neptune, at its closest approach. At that closest approach, S2 is moving at roughly 3% of the speed of light. The combination of its proximity to the black hole's gravity and its orbital velocity produces a measurable time dilation relative to Earth. Astronomers have actually detected the gravitational redshift of light from S2 as it approaches the black hole, one of the most direct observations ever made of general relativistic effects outside the solar system. For S2 itself, if it were a clock rather than a star, the proper time running at its closest approach would be noticeably slower than the proper time on Earth. Not dramatically, S2 is still far from the event horizon, but measurably. Now, think about what lies at the actual event horizon of Sagittarius A star. Objects, gas, dust, disrupted stars are constantly falling toward it. As they approach, their clocks are running slower and slower relative to ours. From our perspective, they never quite reach the horizon. They slow down, redshift, fade. The last light we receive from them was emitted when they were still just outside the point of no return, stretched and dimmed by the extreme time dilation. Inside the horizon, whatever time means, and inside the event horizon, the usual relationship between space and time is inverted in ways that make our ordinary vocabulary of past, present, and future unreliable. It is no longer in any communication with our experience of the universe. There is a concept in cosmology and in the physics of black holes called the last scattering surface, the boundary from which the oldest light we can observe was emitted. But there is an analogous concept for time dilation that is worth sitting with tonight. Imagine drawing a map of the universe in terms not of distance but of time rate. Close to Earth, in the weak gravity and modest velocities of the inner solar system, the time rate is close to what we experience. Move outward into interstellar space, far from any mass, and time runs slightly faster. The gravitational component of time dilation is reduced. Move toward a massive star and time slows. Move toward a neutron star, the densest ordinary matter object in the universe, a stellar remnant with the mass of 1 to 2 suns compressed into a sphere roughly 20 kilometers across, and time slows dramatically. At the surface of a neutron star, gravity is so extreme that time runs at roughly 70% of the rate it does far from the star. For every 10 seconds you experience on a neutron star's surface, roughly 14 seconds pass in the external universe. A neutron star's gravity is not exotic in the way a black hole's is. It doesn't have an event horizon, doesn't trap light, doesn't produce infinite time dilation, but it is extraordinary by any other standard. Neutron stars are essentially the last stable state of matter before the final collapse into a black hole. Objects so dense that a teaspoon of their material would weigh roughly 4 billion tons. And the time dilation at their surface is not a marginal GPS-style correction. It is a genuine, significant distortion of the temporal landscape. Now, move closer to a black hole than any neutron star's surface allows. Move to within a few Schwarzschild radii. And the time dilation leaves behind everything that human intuition has a framework for. It becomes not a physical fact about the universe that you can intellectually acknowledge and move on from, but a fact that, if you truly hold it in your mind, rewrites the emotional content of what it means to exist in time. You are lying somewhere right now, listening to this, and outside your window the universe is running forward at the rate it always has, 1 second per second, steady, reliable, the background rhythm of all experience. And at the same moment in the accretion disk of Sagittarius, a star 26,000 light-years away, matter is spiraling toward an event horizon where the ratio of its experienced time to your experienced time approaches 0. The same moment, different rates, both real. The universe does not have a single tempo. It has as many tempos as it has locations, and the range of those tempos spans from nearly our own, in the quiet, far reaches of intergalactic space, to the infinite, at the edge of the longest lasting structures in the universe. Before we leave black holes and move toward the deep future, let's talk about one more dimension of the clock problem near these objects, because it has implications for the countdown that underlies the entire arc of this video. Black holes evaporate. This was the discovery of Stephen Hawking in 1974, derived from the application of quantum mechanics to the event horizon of a black hole. The mechanism, now called Hawking radiation, is subtle and deeply counterintuitive, but the conclusion is clear. Black holes are not eternal. They slowly lose mass by radiating energy. The rate of loss is inversely proportional to the mass of the black hole. Smaller black holes evaporate faster, larger ones far slower. For a stellar mass black hole of 10 solar masses, the evaporation time is approximately 2 times 10 to the power of 74 years. That is a number so large that it makes the current age of the universe look like a rounding error. The universe is approximately 13.8 billion years old, roughly 10 to the power of 10 years. The evaporation time for a 10 solar mass black hole is 10 to the power of 74 years, 64 orders of magnitude longer than the current age of the universe. For a supermassive black hole like M87 star, 6.5 billion solar masses, the evaporation time scales with the cube of the mass, pushing the timeline to something in the range of 10 to the power of 100 years. And for the most massive black holes we know of, TON 618 at 66 billion solar masses, the evaporation time extends to timescales that we cannot currently express in human language without inventing new vocabulary for the purpose. These are the last clocks in the universe, the last massive objects that will structure the time landscape of the cosmos. Everything else, every star, every planet, every nebula, every galaxy will have long since faded, fragmented, or been consumed. The black holes will remain. Slowly, inexorably, Hawking radiating their mass back into a diffuse sea of low-energy photons and particles, the last concentrations of curved space-time in an increasingly smooth and featureless cosmos. And near those final black holes, in their last flickering moments of existence, time will still be running at a different rate than it runs in the empty space surrounding them. The final clock distortion in the universe will be the last whisper of a black hole giving up its last quantum of mass. When that happens, when the last black hole completes its evaporation and the last event horizon dissolves into a flash of Hawking radiation, the last local distortion of time in the universe will have ended. What remains will be a universe of perfect homogeneity, near zero energy density, maximum entropy. A universe where nothing happens and therefore nothing to measure time against. A universe where the clock, finally, has no one left to tick for. But between here and there lies something that may be even harder to comprehend than black hole time dilation. The way time behaved at the very beginning of the universe, in the first moments after the Big Bang, when the conditions were so extreme and so alien to anything in our current cosmos, that physicists are not entirely certain whether the concept of time as we understand it even applied. And then we are going to fast forward through the timeline of the cosmos, through the stelliferous era of stars and galaxies, through the degenerate era of cold white dwarfs and neutron stars, through the black hole era of the last great concentrations of mass, and we are going to watch what time does to itself over the full arc of cosmic history, because the universe has a timeline, it has phases, it has a beginning that we can partially describe, a middle that we are currently living in, and an end that physics predicts with cold, precise, patient certainty. And understanding what time does at each phase of that timeline is what transforms the universe from a collection of beautiful objects into something more unsettling and more astonishing than any single object within it. It transforms the universe into a clock with a known start time, a known mechanism, and an end state that has been calculated. We know, within the limits of current physics, how this ends. Stay with us. 10 to the power of negative 43 seconds. Write that out as a decimal and you get a 0, followed by a decimal point, followed by 42 more zeros, followed by a 1. It is a duration so short that it has no analogue in any physical process you have ever observed or ever will observe. A single heartbeat lasts roughly 1 second. A single nerve impulse takes about 1,000th of a second. The fastest chemical reactions in biology occur in the range of 1/1,000,000th of a second. The shortest laser pulses ever generated by human technology last about 50 attoseconds. 50 times 10 to the power of negative 18 seconds. Each of those numbers is extraordinarily short. Each of them is longer than 10 to the negative 43 seconds by a margin that staggers the imagination. 10 to the negative 43 seconds is called the Planck time. It is named after the German physicist Max Planck, and it represents something specific and profound. It is the shortest interval of time that current physical theory has any meaningful framework to describe. Below the Planck time, the known laws of physics do not apply, not because we haven't looked hard enough, not because our instruments aren't sensitive enough, but because at scales smaller than the Planck time and the associated Planck length, roughly 10 to the negative 35 meters, the two great pillars of modern physics, quantum mechanics and general relativity, contradict each other in ways that have not been resolved. The mathematics breaks down, the predictions become nonsensical. The theory, confronted with its own limits, returns an error. What happened before the Planck time? In the first 10 to the negative 43 seconds of the universe's existence is, in the most rigorous scientific sense, unknown. Not uncertain, not roughly known, not known within error bars. Unknown. Physics, as currently formulated, cannot reach into that interval and say anything reliable about what was happening to matter, energy, space, or time. Which means that the very first moment of the universe, the moment from which all subsequent time flows, is a moment that time itself, as we understand it, may not have existed yet. Let's think about what that means, because this is not a philosophical game. This is physics confronting a genuine boundary in its own foundations. The universe we currently inhabit is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the current universe, at current temperatures and energy densities, these four forces are distinct. They behave differently. They have different strengths, different ranges, different carrier particles. They are four separate things. But as you go back in time, as you approach the Big Bang and the temperature and energy density of the universe increase toward extreme values, these forces begin to merge. At energies roughly achievable by current particle accelerators, the electromagnetic force and the weak nuclear force are known to unify into a single electroweak force. This unification has been experimentally confirmed. At higher energies, far beyond what any current or planned accelerator can reach, theoretical physics predicts that the strong nuclear force merges with the electroweak force in what is called grand unification. And at the Planck scale, the expectation, though unconfirmed and theoretically incomplete, is that gravity itself merges with the other forces into a single, unified, fundamental interaction. In that state, the state of the universe in the first Planck time, there would be no distinction between the forces. There would be no atoms, no particles as we know them, no structured matter of any kind. There would be an extraordinarily hot, extraordinarily dense, extraordinarily simple state from which everything that currently exists, every galaxy, every star, every planet, every human being, every second of every clock, eventually emerged. And in that state, the relationship between time and space was almost certainly not what it is now. Some theoretical frameworks, most notably Stephen Hawking and James Hartle's no-boundary proposal, suggest that in the quantum gravity regime near the Planck time, the distinction between time and space breaks down. Time becomes, in a mathematical sense, indistinguishable from a spatial dimension. There is no singular starting point, no moment of creation in the conventional sense. Instead, the universe simply is in a four-dimensional geometry that has no preferred time direction and no boundary in time any more than a sphere has a geographic North Pole as a boundary in space. If this picture is correct, And it is important to be clear that it is a theoretical proposal, not an established fact. Then asking what happened before the Big Bang is like asking what is north of the North Pole. The question contains a false assumption. There is no before, not because time had a beginning in the sense of a wall you could run into, but because the concept of before requires a time dimension pointing in a specific direction, and in the quantum gravity regime, there is no such thing. Time in the first moment of the universe was not yet time as we know it. It was something else. Something that, over the subsequent expansion and cooling, crystallized into the one-directional, smooth, continuously flowing river of moments that you have been swimming in every second of your life. The clock did not just start at the Big Bang. The clock became itself at the Big Bang. Let's follow the universe forward from that point, because what happens next is a sequence of phases that transform the cosmos from a state of maximal energy and minimal structure to a state of minimal energy and maximal structure, and then, over unimaginably long timescales, back toward minimal structure again. In the first fraction of a second after the Planck time, the universe underwent inflation, an extraordinarily rapid expansion that stretched the cosmos from a subatomic scale to something roughly the size of a grapefruit in an interval estimated at somewhere between 10 to the negative 36 and 10 to the negative 32 seconds. The expansion was not the movement of matter through space, it was the expansion of space itself, carrying matter along with it, and it proceeded at a rate far exceeding the speed of light, which is permitted because the speed of light limit applies to the motion of objects through space, not to the expansion of space itself. During inflation, the temperature of the universe dropped precipitously. After inflation ended, the energy stored in the inflaton field, whatever drove the expansion, was converted back into a hot, dense plasma of fundamental particles and radiation in a process called reheating. The universe, now something on the order of a centimeter across and cooling rapidly, was filled with quarks, antiquarks, gluons, leptons, photons, and the other fundamental constituents of matter, all in thermal equilibrium at temperatures exceeding 10 to the power of 27 degrees Kelvin. In the first second after the Big Bang, the universe cooled enough for quarks to bind together into protons and neutrons. In the first 3 minutes, the temperature dropped to the point where protons and neutrons could fuse into the lightest atomic nuclei, hydrogen, helium, and trace amounts of lithium. This is Big Bang nucleosynthesis, and the ratio of hydrogen to helium it produced, roughly 3 to 1 by mass, is a prediction of the standard cosmological model that has been confirmed by observation. For the next 380,000 years, the universe remained a hot, opaque plasma of nuclei and electrons, so dense that photons could not travel freely. They were constantly absorbed and re-emitted, bouncing around in an impenetrable fog of charged particles. Time was passing, structure was forming in the density fluctuations seeded by inflation, but the universe was invisible, a glowing, opaque wall in every direction. Then, 380,000 years after the Big Bang, the universe cooled to roughly 3,000 degrees Kelvin, cool enough for electrons to combine with nuclei and form the first neutral atoms. This is called recombination, and its consequence was sudden and dramatic. The universe became transparent. Photons that had been trapped in the plasma were released, streaming freely in all directions. Those photons are still traveling today, cooled by 13.8 billion years of cosmic expansion to a temperature of about 2.7 degrees Kelvin. The cosmic microwave background radiation, the oldest light in the universe, detectable today in every direction of the sky. The moment of recombination was the moment the universe's clock became readable from the outside. Before recombination, the universe kept its own time in total opacity. After recombination, the record became available, written in light, preserved in the microwave background, readable by radio telescopes built by creatures who would not exist for another 13 billion years. From recombination, the universe entered what cosmologists call the cosmic dark ages, a period of roughly 100 to 150 million years, during which the universe was filled with neutral hydrogen and helium gas, gradually cooling and clumping under gravity, but not yet lit by any stars. There was no visible light. The universe was dark and cold and patient, waiting for the density perturbations inherited from inflation to grow large enough under gravity to collapse into the first structures. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars ignited. These first stars, called population 3 stars, a designation that reflects their position in the hierarchy of stellar generations, were fundamentally different from the stars we see today. Formed from pure hydrogen and helium with essentially no heavier elements, they are believed to have been extraordinarily massive, potentially hundreds of times the mass of the Sun, and extraordinarily hot and luminous. They burned through their fuel in millions of years rather than billions, dying in spectacular explosions that seeded the surrounding gas with the first heavy elements ever created outside the Big Bang itself: carbon, oxygen, silicon, iron, all forged in stellar cores and scattered by supernova explosions into the interstellar medium. Every atom of every element heavier than helium in your body was created inside a star. The carbon in your DNA, the oxygen in your lungs, the iron in your blood, all of it was synthesized in stellar cores over billions of years of cosmic history before the solar system existed, scattered by supernova explosions, incorporated into the molecular cloud that collapsed to form the sun and planets, and eventually assembled by the patient processes of chemistry and biology into you. You are, in the most literal, physical sense, the universe examining its own history. We are now approximately 13.8 billion years after the Big Bang, living in what cosmologists call the stelliferous era, the age of stars. This era began with the first stellar ignitions and will end, roughly 100 trillion years from now, when the last red dwarf star exhausts its nuclear fuel and the universe goes dark. 100 trillion years is 10 to the power of 14 years. The current age of the universe, 13.8 billion years, is approximately 1.4 times 10 to the power of 10 years. We are currently about 1/10,000th of the way through the stelliferous era. The age of stars is overwhelmingly in the future, not the past. We are, cosmologically speaking, in the very early morning of the epoch of stellar light. The stars lighting the night sky right now are not the old, tired remnants of a universe in its twilight. They are early arrivals in a story that has barely begun. The era of starlight stretches forward from tonight, for a duration that makes all of recorded human history, all 10,000 years of agriculture and writing and cities and empires and technology, look like a fraction of a second in a year-long film. But the stelliferous era will end. The last stars to die will be the smallest, most miserly red dwarfs, stars with masses around 8% of the Sun's mass, burning their hydrogen so slowly and so completely that their lifetimes extend to trillions of years. When the last of these dim, cool, patient stars exhausts its fuel and fades, the curtain falls on the era of starlight, and the universe enters a new phase. After the last stars die, the universe will not be empty. It will be filled with the cold remnants of stellar evolution, white dwarfs, neutron stars, and black holes, along with vast quantities of brown dwarfs, which never ignited, and free-floating planetary bodies ejected from their star systems over the preceding trillions of years. This era is called the degenerate era, and it will last from roughly 10 to the power of 14 years to roughly 10 to the power of 40 years. In the degenerate era, the dominant objects in the universe are white dwarfs, the Earth-sized, roughly sun-massed remnants of stars like our Sun that have shed their outer layers and left behind their inert, electron-degenerate cores. White dwarfs are not generating energy through nuclear fusion. They are simply cooling, slowly radiating away the thermal energy stored in their interiors, growing dimmer and cooler over trillions of years until they become what are sometimes called black dwarfs, objects so cold they emit essentially no light. Here is a sobering fact about black dwarfs. None currently exist. The universe is not old enough. Even the white dwarfs formed from the earliest stars in the universe, those that lived and died within the first billion years, have not had time to cool to true blackness. The cooling time for a white dwarf to reach near absolute zero temperatures is estimated to be on the order of 10 to the power of 15 years. The universe is currently 10 to the power of 10 years old. We are 5 orders of magnitude, 100,000 times, too young for even one black dwarf to have formed yet. The degenerate era is where time begins to mean something genuinely alien. On timescales of 10 to the power of 15 years, proton decay, if it occurs, which current theory predicts but has not yet been confirmed experimentally, would dissolve ordinary matter. The protons and neutrons that make up every atom in the current universe would spontaneously decay into lighter particles, positrons, neutrinos, photons. If proton decay happens on this timescale, the white dwarfs and neutron stars and cold planetary bodies of the degenerate era would gradually dissolve, their substance radiating away as the fundamental constituents of atomic nuclei ceased to be stable. If proton decay does not occur, if protons are genuinely stable as some models predict, then white dwarfs persist until quantum tunneling processes cause them to transform into black holes or iron-nickel spheres over timescales of roughly 10 to the power of 65 to 10 to the power of 130 years. These are timescales that have no meaningful analogue in anything we have discussed so far tonight. They exceed the evaporation time of stellar mass black holes. They are so long that the current age of the universe is to them as a single Planck time is to the current age of the universe. In these eras, time continues to pass. Clocks, if any existed, would continue to tick. But there would be nothing in the universe capable of building or reading a clock. There would be no thermodynamic gradients large enough to power a civilization. There would be no chemistry capable of supporting biology. There would be no minds to experience the seconds ticking past. Time would be passing for no one. After the degenerate era comes the black hole era, the phase of cosmic history dominated by the supermassive black holes that anchored galaxies during the stelliferous era, and that persist long after everything else has faded. In the black hole era, the universe is nearly empty. Space is expanding, driven by dark energy, at an accelerating rate. The distances between the remaining black holes are growing. The temperature of the universe is dropping toward absolute zero. The cosmic microwave background, already cold at 2.7 Kelvin today, will have cooled to temperatures so low they require scientific notation to express. Temperatures measured in fractions of a degree above absolute zero, so small they are effectively indistinguishable from zero to any physical process. And yet, the black holes persist, patient, silent, slowly evaporating via Hawking radiation. They are the last concentrations of mass and curved space-time in the universe. Near them, time still runs at a different rate than it runs in the surrounding emptiness. The last time dilation gradients in the universe are written in the geometry of their event horizons. The evaporation of a supermassive black hole of 1 billion solar masses, a modest supermassive by the standards of the current universe, takes roughly 10 to the power of 83 years. The evaporation of M87 star's black hole at 6.5 billion solar masses takes roughly 10 to the power of 96 years. Ton 618 at 66 billion solar masses evaporates on a timescale approaching 10 to the power of 100 years, a Google years, the number that the word Google was invented to name. As each black hole evaporates, the final seconds of its existence are marked by an acceleration in the evaporation rate. Hawking radiation becomes stronger as the black hole loses mass because smaller black holes radiate more intensely than larger ones. In the final moments before a black hole evaporates completely, it releases its remaining mass in a burst of high-energy radiation. A final flash, a last pulse of light in a universe that has been dark for unimaginable epochs. Then, the horizon dissolves. The singularity, if it ever truly existed in the way classical general relativity predicts, is resolved by quantum processes we do not yet fully understand. And the region of space-time that was once a center of extreme time dilation becomes indistinguishable from the surrounding void. When the last supermassive black hole completes its evaporation, the black hole era ends. There are no more massive concentrations of matter. There are no more event horizons. There are no more regions of curved space-time. There are no more time dilation gradients of any kind anywhere in the universe. Time still passes, but it passes at the same rate everywhere. The topography of time, the varied landscape of fast and slow clocks that has characterized every region of the universe since the first mass, condensed from the primordial plasma, is flat. The universe has become, in the deepest possible sense, monotonous. What remains after the black hole era is called the dark era, and it is the final phase of the universe as physics currently understands it. In the dark era, the universe contains only the waste products of everything that came before, photons of extraordinarily low energy, neutrinos, electrons, positrons, and a scattering of other stable or quasi-stable particles, all separated by distances so vast that the probability of any two of them ever interacting approaches zero. The temperature of the universe asymptotically approaches absolute zero. The entropy of the universe approaches its maximum value, a state of perfect thermodynamic equilibrium in which no energy gradient exists anywhere to drive any physical process. This is what physicists call the heat death of the universe. It is not death by heat, not a conflagration. It is the death of all temperature differences, all pressure gradients, all chemical potentials. It is the state in which the universe contains the maximum possible disorder, uniformly distributed, with no pockets of order remaining to be exploited by any physical or chemical or biological process. In this state, nothing happens, not because nothing is there, but because nothing can happen, because all the thermodynamic arrows that point events in a direction, that give processes a before and an after, have been erased. There is no way to extract work from the environment. There is no way to build structure. There is no way to store information. There is no way to measure time, because measuring time requires a physical process, and all physical processes require an energy gradient, and there are none. Time passes, technically, in the sense that the mathematical structure of space-time continues to extend into the future, but there is nothing to experience it, nothing to mark it, nothing to define the difference between one moment and the next in any physically meaningful way. The clock continues to tick, but the universe is no longer listening. And here is the final, deeply strange implication of everything we have explored tonight. The thought that sits at the bottom of the full arc of cosmic time and waits for you to find it. We began this video with a GPS satellite and 38 microseconds. We moved through the Moon and Mars and the outer solar system. We travelled to nearby stars and felt the twin paradox in our bones. We stood at the edge of black hole event horizons and watched time approach zero. We went back to the Planck epoch, where time was not yet itself, and we followed the universe forward through 100 trillion years of stars and a googol years of black holes to the final silence of heat death. And throughout all of that, through all those scales, all those environments, all those extremes, one thing was always true. Time was always local. Time was always proper. Time was always the clock that belonged to whoever or whatever was doing the experiencing in the specific gravitational field, at the specific velocity, in the specific moment of the universe's history of that experiencer. There was never a universal clock. There was never a master timer counting out the seconds for everyone simultaneously. There was never a shared now that extended across the cosmos and said, "This is the present, for everyone, everywhere." There was only the particular, the local, the proper time of each thing that existed in a specific place and a specific configuration of space-time, your proper time, running at the rate it runs here tonight, in this gravitational field, at this orbital velocity, at this moment in the 13.8 billion year history of the universe. And that is not a diminishment. It is not a way of saying your time doesn't count, or that your seconds are less real because they are local. It is the opposite. Your seconds are all you have, and they are genuinely, irreducibly yours, not shared with a universe that experiences them differently, not exchangeable with the seconds of a clock on the other side of an event horizon, not interchangeable with the seconds of a civilization that will exist after the last star dies. They are yours. They are happening right now. And the universe is vast enough and old enough and strange enough that the fact that they are happening at all, that the thermodynamic arrow of time in this particular corner of the cosmos has produced something capable of lying in the dark and listening to the story of its own existence, is, when you sit with it long enough, the most astonishing fact in the history of the universe. Not the black holes, not the Planck time, not the heat death. You, listening, now. In the final part of this journey, we are going to bring everything together. We are going to ask what this all means for the specific countdown that defines this channel. The countdown not just to any cosmic event, but to the moment when time as a meaningful, experienced, structured phenomenon ceases to exist anywhere in the universe. We are going to build the complete timeline from the Planck epoch to the last Hawking flash of the last black hole, and we are going to mark every phase, every transition, every deadline. We are going to look at what physics says about whether anything survives beyond the heat death, whether any structure, any information, any echo of the current universe persists into the dark era. And we are going to sit with the number that sits at the end of the timeline, not with fear. With the particular calm that comes from understanding something enormous and true, the calm that this channel has always been about, the calm of lying in the dark and knowing where you are in the story. We are near the beginning. The clock has barely started, and the universe has given us, improbably, the awareness to know it. Let's build the clock, not metaphorically, not as a thought experiment. Let's actually construct the timeline, the full arc, from the first measurable moment of the universe's existence to the last, and mark every phase, every transition, every deadline with the precision that physics currently allows. Because one of the most remarkable things about the universe we inhabit is that it is not opaque to investigation. It is not sealed against understanding. The same physical laws that govern the motion of the pen on your nightstand and the turning of the earth beneath you extend, with extraordinary experimentally verified accuracy, across 13.8 billion years of history in one direction, and across timescales so vast they have no name in common language in the other. The universe has left us enough clues that we can, within the limits of current knowledge, write the timeline. Not guessing, not mythology, physics. So here it is, 10 to the negative 43 seconds after the Big Bang, the Planck epoch, the beginning of what physics can reach, temperature 10 to the power of 32 degrees Kelvin, density 10 to the power of 97 kilograms per cubic meter. The four fundamental forces are unified into a single interaction. Space and time are not yet distinguishable from each other in the way they will be in all subsequent epochs. Quantum gravitational effects dominate everything. The universe is smaller than a single proton. This is the first entry on the timeline. Everything else follows from it, 10 to the negative 36 seconds. Inflation begins. The universe undergoes exponential expansion, doubling in size roughly every 10 to the negative 38 seconds, for a period lasting until approximately 10 to the negative 32 seconds. In this brief interval, the observable universe expands from a scale far smaller than a proton to roughly the size of a grapefruit. Quantum fluctuations in the inflaton field are stretched to macroscopic scales, seeding the density variations that will eventually become galaxies, clusters of galaxies, and the large-scale structure of the cosmos. Everything you have ever seen with your eyes, every star in the night sky, every galaxy in the deepest astronomical images ever taken, traces its origin to density fluctuations born in this fraction of a second, 10 to the negative 12 seconds. The electroweak symmetry breaks, the electromagnetic force and the weak nuclear force, which were unified at higher temperatures, separate into two distinct interactions. The Higgs field acquires its vacuum expectation value. Fundamental particles acquire mass. The universe now has four distinct forces, and the particle physics governing all subsequent history is established. 1 microsecond. Quarks and gluons, which had been moving freely in a quark-gluon plasma, cool enough to be confined into hadrons, protons, and neutrons. The fundamental constituents of atomic nuclei are forming for the first time. The universe is about 1/4 of a second old and already assembling the building blocks of chemistry. 1 second. Neutrinos decouple from the rest of the matter and radiation in the universe, streaming freely ever after as what will eventually become the cosmic neutrino background, an undetected but theoretically predicted relic of the first second that fills the universe today, just as the cosmic microwave background does, but far harder to observe because neutrinos interact so weakly with matter. In this same second, electron-positron pairs are annihilating in great numbers, transferring their energy to photons and slightly heating the photon background relative to the neutrino background. The universe, 1 second old, is already differentiated, already complex, already keeping multiple kinds of records simultaneously. 3 minutes and 46 seconds. Big Bang nucleosynthesis ends. In the preceding few minutes, the universe was hot and dense enough for nuclear fusion, the same process, powering every star in the sky, to proceed freely throughout the cosmos. In this brief window, approximately 75% of the ordinary matter in the universe was fixed as hydrogen and 25% as helium, with trace amounts of deuterium and lithium. The ratio of these elements predicted by the standard cosmological model has been confirmed by observations of the oldest, most pristine gas clouds in the universe to extraordinary precision. In less than 4 minutes, the elemental composition of the universe was set for the next several billion years. 380,000 years. Recombination. The universe cools to approximately 3,000 degrees Kelvin, the temperature at which electrons can stably bind to nuclei without being immediately stripped away by high-energy photons. The universe becomes transparent for the first time. The photons released at this moment travel freely ever after, cooling as the universe expands, becoming the cosmic microwave background we detect today at 2.7 degrees Kelvin. Simultaneously, the density fluctuations in the now neutral gas begin to grow under gravity without being smoothed out by radiation pressure. The seeds of all large-scale structure, all galaxies, all clusters, all the cosmic web begin to germinate. The universe has just become observable in principle to any sufficiently advanced civilization that might arise within it, 100 to 200 million years. The cosmic dark ages end. The first stars ignite. Population 3 stars, massive, hot, short-lived, begin burning hydrogen for the first time, flooding the universe with ultraviolet radiation that rionizes the surrounding neutral hydrogen gas. The universe transitions from the neutral, dark, cold fog of the Dark Ages to the beginning of the structured, lit, chemically evolving cosmos we recognize. The era of starlight begins. The clock, from this point, begins to tick in a medium we can look at. Approximately 1 billion years. The first galaxies are assembling. Supermassive black holes are forming at their centers, growing rapidly by consuming surrounding gas and merging with other black holes. Quasars, the luminous accretion disks surrounding these rapidly growing supermassive black holes, are the brightest objects in the universe at this epoch, visible across cosmic distances. The cosmic star formation rate, the total rate at which new stars are being born across the entire observable universe, is climbing toward its peak, approximately 3 billion years. The cosmic star formation rate reaches its peak. More new stars are being born per year in this epoch than at any other time in cosmic history, before or after. The universe is at the height of its productivity, assembling the stellar populations that will constitute most of the stars ever formed. The galaxy that will become the Milky Way is assembling through mergers and accretion, building up the disk and halo structure that will eventually host a solar system, a planet, and a species that will wonder where it came from. Approximately 4.6 billion years ago, 9.2 billion years after the Big Bang, the solar system forms from the collapse of a molecular cloud enriched by multiple generations of stellar nucleosynthesis. The Sun ignites. The planets accrete from the surrounding disk. Earth forms, differentiated into core, mantle, and crust within the first 100 million years. Within roughly 400 million years, life, in the form of single-celled microorganisms, appears in Earth's oceans. The clock that has been running for 9 billion years has, in one corner of one galaxy, produced something that metabolizes and replicates. Now, 13.8 billion years after the Big Bang, you are here. One species, one planet, one solar system in one galaxy among an estimated 2 trillion in the observable universe. The universe is approximately 9.3 billion light-years in radius out to the edge of the observable region. The distance light has had time to travel since recombination. Beyond that radius, space exists, but its light has not had time to reach us. The universe is still in its stelliferous era, still building and burning stars, still constructing the chemical and thermodynamic gradients that make complexity possible. You are, by any reasonable measure, near the beginning of the story. Now, let's go forward, because the timeline does not end here, and the clock does not stop. 1 billion years from now. The Sun's luminosity has increased by roughly 10% relative to today. This is a consequence of the gradual increase in helium abundance in the Sun's core as hydrogen is consumed by fusion. Helium is a less efficient fuel, so the core contracts and heats slightly to maintain pressure, and the increased temperature drives a higher luminosity. 10% more solar luminosity translates to a significant increase in Earth's surface temperature. The long-term carbon cycle, the geological process by which carbon dioxide is drawn down from the atmosphere and locked into carbonate rocks, will have lowered atmospheric carbon dioxide concentrations to levels at which most plant life can no longer photosynthesize effectively. Complex, multicellular life on Earth faces a fundamental constraint. 1 billion years. That is the window. Not a comfortable, open-ended future in which civilization can grow without limit, but a window of roughly 1 billion years before the habitability of Earth for complex life is fundamentally compromised by the very star that made life possible in the first place. 1 billion years sounds generous on human timescales, on civilizational timescales. It is effectively infinite. Human civilization has existed for 10,000 years. 1 billion is 100,000 times that. There is no useful way to plan for a billion-year timeline from where we currently stand. But it exists. The clock is running. And it is worth knowing that the window is not infinite, because knowing the window exists changes what it means to be inside it. 5 billion years from now, the Sun exhausts the hydrogen in its core and begins fusing hydrogen in a shell around the core. The core contracts. The outer layers expand. The Sun becomes a red giant swelling to roughly 200 times its current radius. Mercury and Venus are almost certainly consumed. Earth's fate depends on the precise mass loss the Sun experiences during the red giant phase. It may be engulfed, or it may narrowly avoid engulfment as the Sun's reduced mass weakens its gravitational hold, and Earth's orbit expands slightly. Either way, Earth's surface is sterilized. The oceans are long gone. The atmosphere has long since been stripped. Whatever was here is no longer here in any recognizable form. The sun then sheds its outer layers in a planetary nebula, leaving behind a white dwarf of roughly half its current mass, an Earth-sized remnant cooling slowly in interstellar space. The solar system, such as it is, continues to orbit this dim, cooling ember. The outer planets persist, cold and dark, their moons frozen, their surfaces unchanged for billions of years. 100 billion years from now. The local group, the cluster of galaxies that includes the Milky Way and Andromeda, along with approximately 50 smaller satellite galaxies, has merged into a single, large, elliptical galaxy. The Milky Way-Andromeda merger, which begins in approximately 4.5 billion years and takes several billion years to complete, is the dominant structural event of our cosmic neighborhood's immediate future. The resulting merged galaxy, sometimes called Milkomeda or Milkdromeda in informal discussions among astronomers, settles into a relaxed, elliptical shape, its spiral structure erased by the violence of the merger. By 100 billion years from now, the universe is entering a period of declining star formation. The reservoirs of cold gas that feed star-forming regions are being depleted. New stars are still forming, but at a rate far below today's. The universe is aging. The stelliferous era is deep into its second half. 1 trillion years from now, 10 to the power of 12 years. The last significant star formation is occurring in dwarf galaxies with residual gas reserves. The Milkomeda galaxy is populated primarily by old, red, dim stars, the long-lived lower-mass members of earlier stellar generations, and the newly formed low-mass red dwarfs that will persist for trillions of years. The universe, seen from outside, would appear dramatically dimmer than today. The brilliant blue-white stars that dominate the night sky in our era are gone. They lived fast and died billions of years ago. What remains is a universe lit by the patient red glow of the most miserly stars ever made. 100 trillion years from now, 10 to the power of 14 years. The last red dwarfs exhaust their fuel. The stelliferous era ends. There are no more nuclear reactions occurring anywhere in the universe. The last star flame goes out. The universe is dark. Let that land for a moment. 100 trillion years from now, the last fire in the universe is extinguished. Not just on Earth, not just in the Milky Way, but everywhere, in every galaxy, in every corner of the observable and unobservable universe. The era that began with the first stellar ignition, 100 to 200 million years after the Big Bang, the era that produced every photon of starlight ever emitted, the era that heated planets and drove chemistry and powered biology, that era ends in darkness, and the clock keeps ticking. 10 to the power of 15 to 10 to the power of 40 years. The degenerate era. White dwarfs cool toward blackness. Neutron stars, no longer heated by accretion, radiate their remaining thermal energy into the surrounding void. Brown dwarfs, objects too small to ever ignite hydrogen fusion, drift silently through intergalactic space. Planets, ejected from their systems over the preceding eons by gravitational interactions, roam freely. The universe is cold, dark, and quiet. In this era, occasional flashes of light punctuate the darkness. White dwarf pairs, brought close together by gravitational radiation losses over enormous timescales, occasionally merge and briefly reignite nuclear fusion in a Type 1a supernova. A last brief blaze before the remnant cools again. These are the last natural fires in the universe, rare, widely separated in space and time, but real. If proton decay occurs on the shorter end of theoretical predictions, around 10 to the power of 34 years, the matter making up white dwarfs and neutron stars begins to dissolve. Slowly, over timescales that dwarf the current age of the universe by 24 orders of magnitude, ordinary matter ceases to be ordinary matter. The protons and neutrons that constitute every atom evaporate into leptons and photons. The last solid objects in the universe dissolve, 10 to the power of 40 to 10 to the power of 100 years. The black hole era. What remains of the universe's mass is locked in black holes of various sizes, the stellar mass remnants of collapsed stars, the intermediate mass black holes formed from mergers, and the supermassive black holes that anchored galaxies for billions of years before the galaxies themselves dissolved. These black holes are the last concentrations of structured space-time in the universe. Near them, time still runs at a different rate than in the surrounding void. The last time dilation gradients are here, faint echoes of the rich topography of gravitational time distortion that once defined every stellar system in every galaxy. Each black hole evaporates via Hawking radiation on its characteristic timescale. Smaller ones go first. A black hole of one solar mass evaporates in roughly 10 to the power of 67 years. Each evaporation is marked by a final burst of high-energy radiation. A brief flash, a momentary brightening of the otherwise featureless darkness, and then silence. The supermassive black holes take far longer. Their evaporation timescales stretch to 10 to the power of 80, 90, 100 years. In the final moments of each evaporation, the black hole loses mass more quickly. Hawking radiation intensifies as the mass decreases, and the final flash is the brightest event that has occurred in the universe in an incomprehensibly long time. A last flare, a punctuation mark at the end of a sentence that began when a star collapsed billions or trillions of years earlier. When the last supermassive black hole, whichever one turns out to be the largest, the most massive, the most patient, completes its evaporation, the black hole era ends. The last event horizon dissolves. The last region of strongly curved space-time becomes indistinguishable from the surrounding void. The last time dilation gradient in the universe disappears. From this moment forward, time passes at the same rate everywhere in the universe. For the first time in the entire history of the cosmos, from the Planck epoch to this moment, there is no place where time runs differently than any other place. The temporal landscape is flat. The clock that has been running differently in different locations since the first density fluctuation of the primordial plasma is now running identically everywhere. Uniform, featureless, infinite, 10 to the power of 100 years and beyond. The dark era. The universe contains only the final decay products of everything that came before, photons of extraordinarily low energy, neutrinos, electrons, positrons, and whatever stable or quasi-stable particles the final Hawking evaporations produced. Space continues to expand, driven by dark energy at an accelerating rate. The distances between the remaining particles grow without bound. The temperature of the universe continues to fall toward absolute zero, asymptotically, never quite reaching it but approaching so closely that the distinction is physically meaningless. Nothing happens. Not because the universe has been destroyed, not because time has stopped, but Because there is nothing left that can happen, no energy gradient to drive a process, no structure to evolve, no information to be processed. The universe has reached maximum entropy. It is, in the thermodynamic sense, dead. And the clock continues to tick, marking seconds in empty space, counting moments that are indistinguishable from each other. Time still passes, but it passes for nothing. Now let's ask the hardest question on the timeline, the one that sits at the very end of the countdown and refuses to resolve cleanly into either comfort or despair. Is this actually the end? Physics gives us several possible answers, and none of them are certain. The first possibility is that the dark era truly is the final state, that the universe expands forever, cools forever, and persists forever in a state of maximum entropy from which no structure ever re-emerges. This is the classical heat death scenario first described by Lord Kelvin and Hermann von Helmholtz in the 19th century and refined by a century and a half of subsequent thermodynamics and cosmology. In this scenario, the timeline has a last meaningful entry, the final Hawking evaporation, and an infinite, uneventful epilogue. The second possibility involves a concept from statistical mechanics called a Boltzmann brain. The physicist Ludwig Boltzmann, grappling with the thermodynamic arrow of time in the 19th century, noted that in an infinite universe in thermal equilibrium, random quantum fluctuations would occasionally, with extraordinary rarity, produce local reductions in entropy. Given infinite time, these fluctuations could, in principle, be arbitrarily large. Given truly infinite time, they could produce, by chance alone, a fully formed human brain, or any other complex structure, complete with false memories of a structured universe, flickering into existence for a moment before dissolving back into equilibrium. These hypothetical constructs are called Boltzmann brains, and they represent one of the most unsettling implications of thermodynamics and infinite time. Given enough time, the laws of probability say that anything that can happen will happen, no matter how unlikely. In a truly infinite dark era, Boltzmann brains would eventually be produced at some extraordinary rate, extraordinarily rare, but non-zero. And in infinite time, non-zero rates of occurrence accumulate to infinite total occurrences. Whether this means anything, whether a Boltzmann brain blinking into existence in an otherwise empty universe constitutes genuine experience or consciousness, or represents anything meaningful, is a question that sits on the boundary between physics and philosophy in a way that resists clean resolution. The third possibility is that we are wrong about the stability of the dark era. Some theoretical frameworks predict that quantum tunneling could eventually cause a false vacuum decay, a phase transition in the quantum field that underlies the structure of spacetime, propagating outward at the speed of light and replacing the existing vacuum with a new, lower energy state. If the current vacuum of the universe is metastable, if there is a lower energy state available, then at some point, in some location, a quantum fluctuation will nucleate the transition, and a bubble of new vacuum will expand outward at the speed of light, reformatting the laws of physics as it goes. If this happens, it would be the end of the current universe in a genuinely final sense. Not just the end of structure, but the end of the physical laws that currently govern existence. And it could happen at any time. There is no warning. There is no countdown. The bubble expands at the speed of light. So it cannot be observed before it arrives. It would not be perceived by anything in its path. The good news, if this perspective offers any comfort, is that current measurements of the Higgs field suggest that the vacuum may be metastable on timescales long enough to encompass everything we have discussed tonight, and then considerably more. The transition, if it occurs, is not imminent on any scale that the word imminent meaningfully applies to. And finally, the fourth possibility, the one that is hardest to evaluate and hardest to dismiss. We do not know that the universe is all there is. We do not know that the Big Bang was a beginning in the absolute sense, the creation of something from nothing. The cosmological models that best fit our observational data are consistent with several different pictures of what, if anything, came before or exists beyond the observable universe. Inflation may be eternal, producing new universes in a vast multiverse of which our observable cosmos is one bubble among an infinite number. The Big Bang may be a bounce, a moment of minimum volume in a cyclically contracting and expanding cosmos that has been doing this forever and will continue forever. The universe may be one of many in a landscape of possible physical laws, most of which do not support structure or life. We do not know. The honest answer is that the edges of the timeline, before the Planck epoch at the beginning and after the final Hawking evaporation at the end, are genuinely, rigorously unknown, not probably known, not roughly known, unknown in the way that the question of what lies north of the North Pole is unknown. The framework for answering the question may not yet exist. What we do know is everything in between, and everything in between is extraordinary. So let's come back to the beginning of this video. Let's come back to the GPS satellite and the 38 microseconds. Let's come back to the clock you were never told about. You are lying somewhere in the dark right now, and outside your window the universe is running forward. Not all at the same rate, not with a single master clock, but forward in a direction defined by entropy, by the arrow of time that points from low entropy beginnings toward high entropy endings, from the structured to the diffuse, from the particular to the uniform. You are 13.8 billion years into a timeline whose next meaningful deadline, the habitability window for complex life on Earth, is approximately 1 billion years away. The window for liquid water on Earth's surface, for the carbon cycle, for the energy gradients that power biology and chemistry and everything that has ever happened on this planet, is roughly 1 billion years. That is the next entry on the countdown. After that, 5 billion years to the sun's red giant phase. Then 100 trillion years to the last star. Then a number approaching 10 to the power of 100 years to the last black hole. Then the dark era, stretching forward without a known end. Against that timeline, the entirety of recorded human history, every empire, every discovery, every act of creation and destruction and love and grief that has ever been written down or remembered or passed from one generation to the next, occupies a span of time so small relative to the full arc of the cosmic countdown that it cannot be seen on any graph with a meaningful scale. It is not even a rounding error. It is a Planck time. And yet, it happened. You happened. Whatever this is, this awareness, this capacity to lie in the dark and hear a story about the universe and feel something about it, happened. In the middle of an unimaginably large timeline in a universe of 2 trillion galaxies, each containing hundreds of billions of stars. On a cooling, rocky planet orbiting a middle-aged star in a quiet, spiral arm, something assembled itself out of the products of stellar nucleosynthesis and became capable of wondering where it came from and where it is going. That is not nothing. In the full accounting of the cosmic timeline, that may be the most remarkable entry of all, more remarkable than the Planck epoch, more remarkable than inflation, more remarkable than the formation of the first stars or the merger of galaxies, or the final evaporation of the last black hole. Because all of those things just happened. They were governed by physics. They proceeded according to the laws written into the structure of space-time from the first moments of the universe's existence. But you, lying there, breathing, listening, are not just a thing that happened. You are a thing that knows it happened. A thing that can trace the timeline backward to the first second and forward to the last. That can feel the weight of the distance between those 2 points. That can understand, in some genuine and irreducible way, what it means to be a clock keeping its own proper time in the middle of a universe that has been keeping time since before time was itself. The GPS engineers corrected for 38 microseconds a day because they took the physics seriously. They did not dismiss the dilation because it was small. They did not round it away because it felt philosophical. They built the correction into the hardware, into the software, into the daily operations of a system used by billions of people. Because 38 microseconds left uncorrected, would accumulate into something that mattered. Your seconds are like that, small, local, proper to you and no one else, running at the rate they run in this gravitational field, at this orbital velocity, at this moment in the 13.8 billion year history of the cosmos. They will not run forever. They will accumulate, as all proper time does, into a sum that is finite and particular and irrepeatable. But they are running right now, and in the full arc of the cosmic timeline from the Planck epoch to the last Hawking flash to whatever, if anything, follows, right now is the only time that any of it means anything to anyone. The universe does not experience itself. It does not sit somewhere outside its own structure and observe the countdown ticking down. The stars do not know they are burning. The black holes do not know they are evaporating. The dark era will not know it has arrived, only here, in the narrow, improbable, fleeting